Why do we need terrestrial reference frames? How do we know the current rate of sea level rise in different regions of the globe? How do ships at sea, aircraft in flight, or self-driving cars know their position accurately enough to ensure a safe arrival at their destinations? How can we quantify deformations and displacements of the Earth's surface that are caused by climate change, natural hazards, plate tectonics, seismic activity, or the melting of ice caps? How do engineers and surveyors determine the correct path of a tunnel during construction, or ensure accurate property boundaries? How do remote sensing analysts determine the position of imagery and data from Earth-observing satellites? How are we able to determine the position of something on the surface of a constantly deforming Earth and compare it to positions determined decades earlier? How can we ever truly understand the dynamic of the planet we call home? The answers to these questions, and many more, all have one thing in common: a terrestrial reference frame. Schematically, a terrestrial reference frame is a gridded mesh with 3 perpendicular axes, x, y, and z, co-moving with the Earth. The intersection of these 3 axes coincides with the center of the Earth, with x and y axes pointing to the equator, and the z-axis oriented toward the North Pole. This framework allows us to communicate the location of any point or object, be it on the Earth's surface or in near space, with 3 values called coordinates, each representing a place on one of the 3 axes. The importance of a terrestrial reference frame is recognized by the United Nations in its General Assembly Resolution, a Global Geodetic Reference Frame for Sustainable Development. This recognizes the growing demand for more accurate positioning services, as well as the economic importance of a global geodetic reference frame and the need to improve global cooperation within geodesy. The terrestrial reference frame is one of a wide variety of geodetic reference products that are provided to the public free of charge by the International Association of Geodesy, or IAG. The IAG works with hundreds of organizations and government agencies around the world to provide positioning and navigation resources that are of vital importance to science and society, and the backbone of all other Earth observation and remote sensing techniques. However, in order to ensure interoperability and consistency of geodetic products, and to fully use various measurements collected by both ground-based sensors and Earth observation satellites, a unique standard reference is required. The International Terrestrial Reference Frame, or ITRF, is recommended not only by the IAG, but also by a number of international scientific organizations, such as the International Union of Geodesy and Geophysics, as a standard reference for Earth science and positioning applications. The ITRF, together with the International Celestial Reference Frame and Physical Height Systems, forms the realization of the Global Geodetic Reference Frame. How is a terrestrial reference frame built? The ITRF is a collaborative international effort built with investments from national mapping agencies, space agencies, universities, and research groups. 4 space geodetic techniques are utilized in the ITRF computation. They are Doppler orbitography and radio positioning integrated by satellite, or DORIS, Global Navigation Satellite Systems, GNSS, Satellite Laser Ranging, SLR, and Very Long Baseline Interferometry, VLBI, which uses radio telescopes receiving signals from distant extragalactic radio sources called quasars. These techniques are organized as scientific services and are part of the structure of the International Association of Geodesy. Realizing the ITRF starts at geodetic observatories, which are located all around the world and feature infrastructure for one or more space geodetic techniques. Data collected at an observatory is then sent to data centers, which, in turn, provide access to this data for analysis and combination. The ITRF is materialized by computing the time-dependent coordinates of more than 1,800 geodetic Earth observation instruments. This task is done with millimeter precision over many years. Integrating the 4 technique networks together in the ITRF requires the availability of sites where 2 or more independent geodetic instruments from 2 or more techniques are operated and geodetically connected. Such co-location sites are fundamental for the realization of the ITRF. Furthermore, merging these different techniques allows the evaluation and validation of the observation quality and accuracy, as well as enabling the generation of other geodetic products. How does the ITRF help us understand our dynamic and deforming Earth? Coordinates in the ITRF are time-dependent due to the constantly occurring changes in our planet's shape. These changes are caused by a number of geophysical processes, such as plate tectonic motions, and are illustrated by the horizontal station velocities of the ITRF solution. Moreover, the ITRF is also used to model, detect, and understand displacements caused by natural hazards and disasters. For example, this helps inform disaster risk reduction efforts for devastating earthquakes, such as events in Chile and Japan, where co-seismic displacements reach more than 3 meters. This information also helps island and coastal communities better understand and reduce their disaster risk. Monitoring of climate change and its associated natural hazards will become increasingly important with time, and Geodesy fundamentally contributes to this goal by providing the reference frames enabling highly accurate Earth observations. At a regional level, reliable access to the global ITRF is needed for science applications and operational geodesy. Regional reference frames are realized through densified networks of GNSS reference stations and mathematically aligned to the ITRF to ensure their interoperability for positioning applications. The maintenance of such regional reference frames is under the responsibility of IAG regional subcommissions: CIRGAS for Latin America, NAREF for North America, URF for Europe, AFREF for Africa, and APREF for both Asia-Pacific and Antarctica regions. The tremendous social benefits of long-term, stable, and accurate reference frames will continue to fuel innovative location-based applications, with all this based on data from 4 different but interconnected geodetic techniques. The next time you use your smartphone for navigation, remember that your position is one point on a vast, international terrestrial reference frame with Geodesy as your guide.